I have to start off with two apologies. First, I will explain. Through circumstances beyond my control, I came on this cruise without my lady fair. As a result, although I have brought with me an incredible number of fancy jackets and trousers and all kinds of accoutrements, I have made up my mind to sort of luxuriate in the freedom of having no female overseeing me and dress exclusively in my oldest costume, just occasionally changing the linen. But today, in honor of our country's birthday, I am dressed in red, white, and blue. But fear not, tomorrow I will be my accustomed Slavish self. The second apology is that some of you may know that I have been singing in red, white, and beautiful. Well, immediately after this lecture, I have to rush down for the third showing. Now, the first show, I managed to get all the notes out. The second show, the first three notes came out in a whisper. And I give you as an exclusive that in the third show, I won't be able to make a sound. But I've got to go down. Oh, you like that? Let's fight, I'll see. But in any case, I will not be able to be my accustomed, gracious self, giving of myself with autographs and smiles and all the rest. I will have to dash. Please forgive me. Tomorrow, once again, graciousness personified. Now, I think that perhaps some of you did not hear my second lecture on the Copernican Revolution. Essentially, I told the story of how the picture of the universe was turned inside out. Instead of having the Earth at the center and all the planets, including the Sun, revolving about the Earth, we have the Sun at the center and all the planets, including the Earth, revolving about it. Now, if we're going to continue the story in 2 lectures more, it is impossible to take up all of astronomy or even a respectable fraction of astronomy. Instead, I'm going to have to pick out one major topic and consider that, and hope that other lecturers in other places and other times on this cruise will cover many of the things that I'm leaving out. The subject that I'm going to discuss is the evolving concepts of the size of the universe. Now, the ancients were able to determine with accuracy, as I explained, the distance of the moon, which is 250,000 miles away. So they thought, and so it is. There was at least one estimate for the distance of the Sun, which came out to be 5 million miles. This is a gross underestimate, but it was the best that was made in ancient times, and nothing until the 1600s improved on it. Even after the Copernican Revolution, even after the telescope had been invented, there still was no way of telling the actual distance of any heavenly body except the moon, and that estimate for the Sun was the best anyone could find. We might suppose that since the Sun is roughly halfway out towards the sky, if we just count the planets, that perhaps it is 10 million miles to the sky with the stars stuck in it, so that the entire diameter of the universe, as it was known to the Greeks, was 20 million miles. I'm going to write 20 million miles on the board. 20 million miles. And I'm going to put parenthesis, Greeks. You should hear Marcy Sigler speaking Greek. She can speak Greek. It's amazing. Such a cow. From the time she was a little baby, she could speak Greek. Now, even as late as the 1600s, there was no reason to think that the universe was more than 20 million miles wide. That is no definite reason. People might speculate, but there was no measurement. What do we need to find out the distance of bodies farther away than the moon? We need to determine the parallax. I mentioned the parallax in an earlier lecture. The parallax represents the change of a nearby object against a more distant background when you look at it from 2 different places. The simplest way you can show this for yourself is to hold your finger up in front of your face and look at it against the wall or any other background, first with one eye, then with the other. And if you do so, you'll see it'll be in two different places. And if you move it further away, you'll see that the jump between the two different places is less. That jump against the more distant object is called parallax. And parallax varies in two ways. The further an object is, the smaller the parallax is. And the greater the distance between the places from which you view it, the larger the parallax is. So if something is so far away that it has a tiny parallax, you look at it more or less simultaneously from two different places that are much farther away than the distance between your eyes. That increases the parallax to the point where perhaps you can see it. Now, in order to really look at something from great distances, say from here and from California, you need, first of all, a clock. Because you have to know that you and your California buddy are looking at the same object at the same time. If you're looking at it now, the other guy is looking at some other time, it has moved in between. And you mustn't assume that what is actually motion is parallax. Unfortunately, in Galileo's time, for instance, there was no such thing as an accurate clock. As a matter of fact, although it's difficult to imagine this, we take clocks so for granted, that there wasn't, until a little over 3 centuries ago, any clock anywhere that could measure time to less than the nearest hour. People generally were satisfied to say, I will see you in the afternoon, or I will see you when the shades of evening fall, or when the sun rises above yonder yardarm, or something like that. No one ever heard of 3:05 p.m. Galileo, when he followed the motions of falling bodies, had to use either his pulse as a timing mechanism, which meant he had to remain equanimous, which was difficult, for he was an excitable gentleman, or else he used a vessel with a tiny hole in the bottom, filled it with water, and had to count the drifts at the same time he was following the object moving, and this wasn't easy to understand. It wasn't until the 1650s that the pendulum clock was invented. The pendulum clock depends upon the fact that a pendulum beats out the same interval with each beat. And if you can fix it up to a set of gears, the gears move click, 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 click very steadily, and if those are fixed up to hands, they move around the clock face very steadily. And with the use of a pendulum clock, for the first time in the history of mankind, time could be measured to the nearest minute and even fraction of a minute. Well, it's particularly ironic that Galileo didn't have a good timepiece, because guess who discovered the principle of the pendulum? Right, Galileo. He did it when he was a young lad of 17. He was attending services at the Cathedral of Pisa, and I think it was rather typical of him that while the services were continuing and the incense was floating in the air and the intonings and the genuflections were going on, that he had his attention centered on a chandelier which was swinging in the currents of air. And he noticed that sometimes it swung through a small and sometimes through a large. But in either case, it seemed to take the same time. And there he was, with all the sermon going on, with one thumb on his pulse, counting. He went home on a run to experiment with pendulums, and found out that was indeed so. Well, not quite so. That's the trouble with science. You work out a beautiful, simple discovery, and you find out that it's not quite so. An ordinary pendulum oscillates in such a way that it's bob, the weight at the bottom. I always call it a bob because I feel familiar with it. I imagine some people might tend to call it a Robert. This bob follows a circular path, or at least a portion of a circular path. And when it follows this circular path, it isn't quite equally periodic with amplitude. A long swing takes a little bit longer than a short swing. Actually, it could be shown that if instead of following a circular path, or a portion of a circular path, it followed the path of a curve called a cycloid, then it would indeed take the same time for every swing, regardless of amplitude. And a Dutch mathematician and physicist, Christian Huygens, figured out a way to force the bulb to move in a cycloidal path. And when that was done, he could take the pendulum, hook it up to the gears, and he invented the first grandfather's clock. And with that, science entered a new phase, because for the first time, there was a method for accurately measuring time. Now, granted that you could measure time accurately, it was still impossible to tell the parallax of any body beyond, of any heavenly body beyond the moon, because it was still too small to detect with the naked eye. You needed an instrument that could expand things, that could make it possible to measure smaller angles. And for that you had the telescope. Well, how then did the telescope and the clock combine to first measure the parallax of a really distant object? It came about in 1671 as follows. At the head of the Paris Observatory was an astronomer named Giovanni Domenico Cassini. That was his Italian name. He went to Paris in middle life, and he is known among the French as Jean-Dominique Cassini. And I have carefully memorized both names to show you how smart I am. He was an excellent observer. He was the most prominent astronomer of his time. He only had one small failing. Whenever a new theory was advanced, Cassini always took the wrong side. Had they but known, they could easily have told which theories were correct by observing what Cassini believed and doing the opposite. Now, there was some question about the shape of the Earth. There was some feeling that the Earth had an equatorial bulge. It was flattened at the pole. Cassini therefore thought the opposite. And of course, to this planet or that, because that changes as it moves in its orbit. And when it's on the other side of the sun, it's much further from us than when it's on the same side of the sun as we are. But the sun itself, which is in the center, is very nearly the same distance from us at all times. So usually, when we want to give the dimensions of the solar system, we work it out at the distance from the Earth to the sun. And according to this parallax of Mars, the distance determined in 1671 was 87 million miles. Actually, that is not quite correct. It's known to be 93 million miles. But you know, for a first estimate, Cassini got very close. And we can assume that it's 93 million. We won't stick to this first estimate. What it amounts to, though, is that it was only in 1671, a full century and a third after the Copernican revolution, that for the first time in the history of mankind had a notion of the true dimensions of the solar system. That for the first time he knew how far away the sun was. And he knew, for instance, that the most distant planet then known, Saturn, was about 880 miles from the sun. So that if the spectrum is further, we get the story of Friedrich Wilhelm Herschel. He was born in Hanover, which was in his time an appanage of the King of Great Britain, who was also Elector of Hanover. And in Herschel's time, by a curious coincidence, the Elector of Hanover and the King of Great Britain was one George III, which is appropriate to the day, right? And in Hanover, there was some danger that Friedrich Wilhelm Herschel would be drafted into the army, and so he thought he would go to Great Britain where there was no conscription. And he went, changed his name to William Herschel, which is as he is now known, took up a post in Bath, a city in England, and took on the job of teaching musical instruments, teaching society ladies how to play musical instruments, which he did very successfully, because he apparently could play musical instruments very well and was also charming to the ladies. And this is a combination I sympathize with. However, like many of us here, William Herschel was interested in astronomy. And what he wanted more than anything else in the world was a telescope, so he could look at the stars and other things. And he couldn't afford a telescope. So he decided to make his own. And he took on the task of grinding the necessary lenses and mirrors or whatever it was he used. And in order to do that, he became very meticulous, called in his sister, Caroline Herschel, from Hanover to help him. Caroline Herschel spent her entire life first helping him and then helping his son, John Herschel, with complete self-abnegation, lived to the great age of 98, and was herself the first woman astronomer of note. Among other things, she discovered 5 comets. However, the thing for which Caroline Herschel is best known to me is for the role she played in the making of the telescopes. Because while William Herschel was polishing and polishing and polishing, he hated to stop once he got the thing going right. And he would get hungry, and what he did while he was polishing was to open his mouth while she popped pieces of food into them. And I said, Carol, this bothers me a great deal. I have read in any number of places about this, and I have this picture of William Herschel not stopping to eat because she fed him. But with my crass mind, I think of other bodily functions, and I don't see how she did it for him. Anyway, he got his telescope. And because he couldn't afford a telescope and had to make his own, he ended up with the best telescopes in the world. Because there's nothing like Teutonic thoroughness. And once he had his telescopes, he began to look at the heavens. He looked at Saturn, he found a couple of new satellites, for instance, and he found double stars for the first time. He found clusters of stars, all sorts of things. And one day, he saw something which without the telescope looked like a faint star, but with the telescope looked like a little round ball. Now, the only thing that looks like anything but a point of light in the telescope are planets and comets. And so he announced he discovered a comet. However, as he watched it, he noticed that unlike comets, it didn't have a fuzzy boundary. It had a sharp boundary, like a planet. And as he checked its motion, he found that it had an orbit that lay outside Saturn at all points. This was not the orbit of a comet, it was the orbit of a planet, and he came to the conclusion he had discovered a new planet. The first discovery of a planet in the history of civilized man. All the previously known planets have been discovered in prehistoric times with the naked eye. Furthermore, this new planet, which he called Georgium Cetus, which means George's star, for which he promptly got a pension from George, but which did not stay, fortunately. It's a rotten name for a planet. The English astronomers wanted to call it Herschel. The French astronomers said, not on your life. And they suggested a mythological name to suit the others, and it's called Uranus. Saturn is the father of Jupiter. Actually, it's Cronus is the father of Zeus, but we use the Latin equivalents. Saturn is the father of Jupiter, and Uranus is the father of Saturn. So we have a nice family arrangement there. Uranus instantly doubled the size of the solar system, because it was like 1,700,000 miles from the sun. Later on, more planets were discovered. In both cases, they're rather interesting, but I won't go into detail on the discovery. When they followed Uranus's orbit around the sun, they noticed that it didn't exactly follow the law of gravitation. In other words, after they counted in all the various pulls on Uranus, the sun's pull and the pull from Jupiter and the pull from Saturn, they figured out where Uranus ought to be as a result of all those pulls. It was a tiny little bit different. So they adjusted their figures and waited, and again it was a tiny little bit different. Either the theory of gravitation was wrong, which no one would admit, or else there was another body pulling at it, which wasn't being taken into account because nobody knew that the body existed. So they tried that out. A young man called John Couch Adams, a graduate student at Cambridge or some English place like that, calculated out where a planet ought to be. He guessed at how far from the sun it might be, how large it might be, and he figured where exactly it ought to be to account for all the differences in Uranus's position from what it should be. And he went to visit the Astronomer Royal of England, Sir George Airy, who was an unfortunate character. He himself was the kind of person who rode roughshod over all his underlings, and when he sent them out to look at an eclipse, he sent with them not only complete instructions for everything, but all their equipment. They weren't able even to brush their hair, I don't believe, without his instructions as to where to put the part. He also had the same faculty that Cassini had for being wrong. He was a lot like Frank Brantley, in other words. Don't tell us, because Frank Brantley's the sweetest guy in the world. I'm lying. Well, Sir George Airy finally received a note from John Couch Adams to the effect that he had a suggestion for a new planet, and Sir George Airy paid no attention at all. And Adams was the kind of non-pushy fellow who didn't follow up. Meanwhile, in France, another gentleman, Urbain Jean-Joseph Le Verrier, made the same calculations and got the same answer. And he went to a gentleman named Gala and said, "Oh boy," he said, "will you look at the sky in such and such a place and see if you can find a new planet?" And it so happened that Gala had just received a new star map of precisely that region in space the day before. Now, when you have a new star map of precisely that region in space, you look at it and it's very easy to see if there's something in the skies that isn't on the map. And it might be that it would be, because if it's a planet, it's moved into there from someplace else. Well, he looked, and the first night he found a new planet, which was later called Neptune. And as soon as that was found, Sir George Airy ordered a search in England, too. Because a British discovery would make it official. And they found the planet also. These days, Le Verrier and Adams share the credit for having found a planet just by calculating things out on a piece of paper, which shows the powers of a correct theory. In 1930, a still further planet was calculated out in the same sort of way by Percival Lowell of the United States. No, it was calculated out in 1960. It was found in 1930. And by a peculiar coincidence, the new planet that was found was not the one Percival Lowell had calculated out. And it didn't account for the changes in the orbits of Uranus and Neptune. But it was there. It was a wrong planet, but it happened to be in the right place, which is called luck. And it's called Pluto. Pluto is still the farthest planet known. We can be pretty certain that the influence of the sun extends beyond it, that there may be other planets beyond it, but even if there aren't, there are certainly comets that reach out farther. But let's go with Pluto. Pluto has an orbit which has a diameter of 7,000 million miles. I'll write that down. 7,000 million miles. That's the present. Now we see that the solar system, as we see it now, is itself like 350 times as far across as the old Greek cube. But the solar system is not all there is to the universe. What about the stars? Now the ancients had thought that there was a more or less solid sky, a sphere, all around the earth, with the stars stuck into it as little dots of light. They look like little dots of light. Why not assume they are little dots of light? The first reason to suppose that they were anything else than little dots of light came about when an English astronomer, Edmund Halley, carefully noted the positions of various stars, just to see if he could prepare a better star map than those that already existed. And he found that at least 3 stars showed positions distinctly different from those they have had, or at least those that have been reported in ancient Greece. They were Sirius, Procyon, and Arcturus. Now, granted, the ancient Greeks did not have telescopes and could only measure distances with only limited accuracy. But they did do it with that limited accuracy, and these stars were further away than could be accounted for by Greek mistakes. It seemed to Halley quite obvious that those stars had moved. Now, when you look at all the stars, or at all the stars that you can measure in a comfortable time, at all the stars that had been located by the Greeks, you find that only a few of them have moved, and they're invariably, apparently, the brighter ones. Now, what does this mean? If some of the stars move, that means they are not fixed to the sky, like luminous thumbtacks. But if some of the stars move, why don't they all move? And it would appear that, let us suppose that all the stars are moving at more or less the same rate. Well, some might be moving away from us, or some might be moving toward us, and we wouldn't see them move, because if I move this way, or I move that way, and all you can measure is movement across the line of sight, it would seem I don't move. But if I move this way, you would see it, and if I move this way, you would see it. However, the further away I am, if I make the same movement, the less noticeable it is. Something close to you that moves only an inch, you can see. Something very far from you that moves only an inch, you can't see. In other words, this proper motion, as you might call it, is characteristic of nearby stars. The nearer the star, the larger its proper motion is likely to be. And actually, it's the brighter stars that show a proper motion. And it might well be that the reason they're brighter is because they're closer to us. So now we have this feeling that the stars are all at different distances. Some are fairly close, some are farther, some maybe are much farther. And we detect the proper motions over a mere few thousand years only for the nearer ones. So that Halley got the notion, which as a matter of fact Nicholas of Pisa had in the 1400s, that the stars were scattered through space, all of them moving randomly like bees in a swarm. And he said to himself, supposing the star Sirius, for instance, were actually as bright as the sun, but that it was far away from us, so far that it was just a little spark of light, no brighter than the star Sirius. He calculated out that in that case, it would be something like 12 trillion miles away. That's 12,000 billion, or 12 million. I specify this because the British have a different way of saying big numbers. What we call 12 trillion, as I just did, they say 12 billion. And I would reason it out for you. But on the 4th of July, I am not going to use the British method. So it's 12 trillion miles. Now, saying 12 trillion miles is difficult because who can conceive 12 trillion miles? I'll write it out here just to show you what 12 trillion looks like. As you see, like so. There should be some way to make a smaller number out of it, just for convenience and speed. Now, the only reason we see a star is by virtue of the light that reaches us. This light travels, we know, at 186,282.3959 miles per second. Pardon me? That's okay. This is the latest figure, if I remember it correctly. This means that if you follow this light ray, it's chased behind you for a solid year, you'll find it will have covered something like 5,880,000,000,000 miles, a little less than 6 trillion miles, which then becomes a light year. So that what Halley was saying was that he thought the star Sirius might be like 2 light years away. Actually, he had the right idea, it was the right ballpark, but he was wrong, actually, because Sirius is brighter than the sun, and to be no brighter than it is in appearance, it would have to be even further than 2 light years. But you know, Halley's suggestion was not in itself convincing, because you had to suppose that the stars were really suns. Maybe they weren't. You either had to prove they were really suns, or you had to measure the distance accurately without that supposition. And the one way you could do it was by parallax. Well now, astronomers had a great deal of difficulty in detecting the parallax of Mars, which is at sometimes only 30 million miles from the Earth. Well now, you compare 30 million to trillions, and you can see that the parallax of a star must be so tiny that if you try to measure the distance of a nearby star against the position of a distant star from Paris and from French Guiana, you'll have nothing. Even with the best telescope in the world, you won't detect the difference. But you don't have to stay on the surface of the Earth, so to speak. The Earth moves around the sun. And at one point, it is 93 million miles to the left of the sun. Half a year later, it is 93 million miles to the right of the sun, so that you can look at the star from points that are 186 million miles apart. You can look at it in January, you can look at it again in July. In fact, you can look at it constantly, and the star will make a tiny ellipse in the sky that sort of mirrors the huge ellipse that the Earth makes around the sun. The only trouble is that even so, that tiny ellipse is too small to measure. For 100 years, in fact more than that, for 300 years, astronomers kept worrying about the parallax of the stars. When Copernicus first suggested that the Earth went around the sun, there were people who objected and said, if the Earth really went around the sun, there would be a stellar parallax. And there wasn't. And the only answer Copernicus could make was that the stars were so far away that they didn't show a parallax large enough to measure. And this was indeed correct, but there was no way of proving it at the time. It sounds like an argument just made up to prove a case. This is called an ad hoc argument, and all honest scientists sneer at it. Well, all through the 1600s and the 1700s, astronomers kept trying to measure very accurately the distance between two stars at different times of the year to see if they changed slightly, in which case the brighter one, which is probably the closer one, would show a parallax and the distance could be measured. And as it happens very frequently in science, once you spend 3 centuries looking and no one finds, eventually 3 people find it at the same time. This is because the instruments improve, theories improve, conditions improve, and the time comes, first that nobody can do it, and then that anybody can do it. Well, as a matter of fact, in the 1830s, 3 astronomers were busy trying to measure the parallaxes of stars. One of them was called Friedrich Wilhelm Bessel in Germany, and he worked with a star called 61 Cygni, which just means that according to a certain system of numbering, the star was the 61st star in the constellation of Cygnus the Swan. Why did he pick 61 Cygni, which is a dim star? And you couldn't suppose from its dimness that it was particularly close. And there's obviously no point in fooling around with a distant star, because the parallax would then be so small that nothing you could do would measure it. Well, the thing was that 61 Cygni moved faster than any other star then known. It changed position in the heavens. 5 seconds of arc a year, actually, which means that, let's see now, 12 times, in 360 years it would move the width of the moon, which is tremendous, astronomically speaking. And he figured that the reason it moved this much was because it must be close. And so he studied it. Meanwhile, in Russia, another astronomer, Friedrich Wilhelm von Schnull, notice all Friedrich Wilhelms. That's because the kings of Prussia in those days were called Friedrich Wilhelm. And a royal name is always good luck. Friedrich Wilhelm von Schnull was studying a star called Vega, which is the 4th brightest star in the heavens. And meanwhile, Thomas Henderson, down in South Africa, a Scottish astronomer, was studying Alpha Centauri, which was the 3rd brightest star in the heavens. And in 1838, Bessel won the Grand Stellar Parallax Handicap. And he announced the parallax of 61 Cygni and showed that it was equivalent to a distance of 11.1 light years. Well, no, that's the present figure. 11 light years is good enough. He was the first man to accurately measure the distance of a star, the first man to prove that the starry sky was very much farther away than any planet, thousands of times as far away as any planet. Furthermore, the very next year, 1839, Henderson announced that Alpha Centauri was 4 light years away. Now, he was second in the race, but he had discovered something. He had found what we now know to be the nearest star to us. Well, the nearest star outside the solar system to us. A kid once asked me, what's the nearest star to us? And I said, Alpha Centauri, as anyone would say. And he said, no, it isn't. He says, the sun is. So I hit him. Rotten kid. Actually, Alpha Centauri is a system of 3 suns. The largest of them is called Alpha Centauri A. The second largest is Alpha Centauri B. And the third largest is, you'll never guess, Alpha Centauri C. Alpha Centauri A is just about the twin of our sun. It's the same size, the same brightness. Alpha Centauri B is a little dimmer, a little smaller. Alpha Centauri C is a very unusual star. It's very small and very dim. It's barely red hot. Even though it is only 4 light years away, we can barely see it with a good telescope. As a matter of fact, at the present moment, you see it rotates around the other two suns, and at the present revolves about the other two suns, and at the present moment it's on our side of the system, so that it's a little closer than the other two, and it's called Proxima Centauri, our neighbor in Centaurus. In 1840, von Struve determined the distance of Vega to be 27 light years. Now, it was not just that these astronomers had detected the distance of stars. They had detected the distance of the nearest stars, of very close stars. And these were light years away, trillions of miles away. Beyond them lay thousands, millions of more distant stars, which showed no parallax at all. They were so far away. To this present time, we can't tell the parallax accurately for any star further than a couple of hundred light years away. And the total number of stars whose parallax we can tell, and which are therefore closer than a couple of hundred light years, are few in comparison to the total number of stars. So that we deduce that the universe must be much larger than just the distance of those nearest stars. Those nearest stars is just the beginning. And the question is the universe infinite? Do the stars just go out and out and out and out forever? Or is it finite? Is it a large collection, but a finite collection of very many stars, but a finite number of stars? And the first person really to address himself to this problem was William Herschel. Now, it so happens that there is in the sky something called the Milky Way, and perhaps in your gazing at stars in the course of this cruise, you have seen it. I personally have hardly ever seen the Milky Way, largely because I live in New York City, where one doesn't even see the stars. The sun is visible as a kind of a dim, murky sphere. Now, Galileo had looked at the Milky Way and had seen it was composed of a vast number of very dim stars. So that you might suppose that in one direction, the direction of the Milky Way, there may be stars stretching very far out, so that all the stars melt into a kind of a dim, luminous blur. Whereas in other directions, away from the Milky Way, there may be a relatively small number of stars, and therefore, it may not stretch out as far. Herschel decided to do this quantitatively and to check the number of stars in all the different directions of the heavens. The simplest way of doing this, in a way, is simply to look in your telescope and count all the stars you can see everywhere. But this would take a long, long, long time. And William Herschel thought he had a better trick than that. He invented statistical astronomy. Instead of looking everywhere, he just selected randomly certain patches of the sky in such a way that every portion of the sky was represented. He took a straw poll of the heavens, a Gallup poll, and he counted the stars in each little segment of all the different levels of... He was not dealing with a kind of sphere of stars. He was dealing with a kind of lens shape of stars. I will draw a lens shape here, which will look like a flat ellipse. And let us suppose that the solar system is here somewhere in the center. If you look out towards the long diameter, you will see many, many, many stars. If you look out towards the short diameter, you will see fewer stars. And therefore, the further away from the Milky Way, the fewer stars you would see. The Milky Way would be around here, around the fat equator of this lens-shaped collection. What do we call it? Well, the Milky Way is the most prominent characteristic. It's what gave Herschel the idea for a shaped body of stars, and the Milky Way in Greek is called Via Galactica. The Milky Way, way Milky. No, that's not in Greek. The first word is wrong. It's Galacticos is in Greek. Via Lactea is in Latin.
My God.
Pardon me?
My God.
No, that's not right. It is? Okay, we'll take it. In any case, the English word we get from Galactica is galaxy. And the galaxy means the Milky Way, really. So we call this the galaxy, and Sir William Herschel discovered the galaxy. He even decided to attempt to guess at what its dimensions might be. And his dimensions, which I have written down here, I think. Okay, he had this, the extreme length, 8,000 light years, Ly, and the thickness, 1,500 light years, and he figured that in it there were 300 million stars. And he did this in 1784. Observe how the size of the universe has increased by 1784. Now we are talking not of a few light years, but of thousands of light years. And naturally, we can be sure that this increased with time. As better star maps were made, better telescopes were made, more accurate star counts were made, it seemed that the galaxy was larger than Herschel had thought, contained more stars, and so on. The size of the galaxy was continually increasing throughout the 19th century. And yet there was one interesting thing about the galaxy. Even though the Earth is no longer the center of the universe, and even though the sun is can no longer be pictured as the huge, immense body which governs the rest of the universe, it just governs the few planets that move around it. And it is lost in a vast galaxy composed of huge numbers of stars, but still it would seem that it is at least located at or near the center of the galaxy. And this is a comfortable place for it to be. It's important to be at the center. You feel somehow the cynosure of all eyes. And the way you can prove that it seems to be at the center of the galaxy is that the Milky Way is roughly equally bright all the way around. If the Earth were at one end, well, the solar system, were at one end of the galaxy, then in one direction, it would look through a vastly greater distance of stars than in the other direction. And you would have the Milky Way very huge in one part of the sky and sort of thin and scattered in the opposite side of the sky, and you would know that the center of the galaxy is in the direction of the huge hunk of Milky Way. But this doesn't happen. The Milky Way is equal all the way around. Everyone was therefore happy with that, except for one thing. If the Earth were really in the center of the galaxy, there'd be all kinds of phenomena that would be evenly scattered over all the sky. And this is not true of one thing. There are globular clusters. In other words, clumps of stars, large numbers of stars from tens of thousands to hundreds of thousands, all looking like a little heap of talcum powder under the microscope. All these stars cling together a sphere of stars. These globular clusters, about 200 of them, 100 of them are easily seen in the galaxy, and you would expect that they would be distributed over all the sky, but they are not. They are distributed very largely in one half of the sky, and not in the other half. In fact, 1/3 of them are located in the single constellation of Sagittarius. There was a question, why the heck are all these globular clusters clustered in that one place? Well, no one can answer that until a new system of measuring distances was determined. And this involved certain variable stars, that is, stars which sort of became brighter and then dimmer and then brighter and then dimmer and then brighter and then dimmer according to a certain pattern. They're called Cepheid variables, Cepheid, because the first one of the type studied was Delta Cephei, the fourth star. Delta is the fourth Greek letter. The fourth star, except that some had in the single constellation, because the first one of the type studied was Delta Cephei, the fourth star. Delta is the fourth Greek letter. The fourth star in the constellation of Cepheus. Well, all these Cepheid variables were alike, except that some had a short period of variation, some a longer period, anywhere from a day to a couple of weeks. 4 or 5 days was the average. And this was interesting, but not terribly significant, until 1912, when a woman astronomer, I say woman because I always like to stress the occasions upon which women do something, despite the... So Henrietta Swan Leavitt studied the stars in the Magellanic Clouds. The Magellanic Clouds appear in the skies of the southern hemisphere and look like detached portions of the Milky Way. They're called the Magellanic Clouds because they were first noted by sailors on the ships of Magellan when he was going around the Earth in 1519 to 1522 and fooling around down there on the southern coast of South America, discovering the Straits of Magellan too. You always name it after Magellan because he was the first person to see it or find it, except for a few thousand Patagonians. Nothing gets counted unless it's a white European who discovers it. Remember that. It's a basic tenet of science. Well, the Magellanic Clouds have Cepheid variables in them. And all these Cepheid variables are approximately the same distance from us. Because the Magellanic Clouds are very far away. We now know them to be 150,000 light years away. They lie outside the galaxy. They're like satellite galaxies. And therefore, it doesn't much matter whether a star is on this edge of the Magellanic Cloud or that edge of the Magellanic Cloud. That makes very little difference compared to the total distance. We can say that everyone in New York City right now is about the same distance from us, whether they're in Staten Island or in the Bronx. That small distance makes no difference much compared to the total distance. Well then, when they studied these Cepheid variables in the Magellanic Clouds, they found that the brighter the variable, the longer the period. Now in the Magellanic Clouds, a Cepheid variable that seemed brighter really was brighter because they were at the same distance. Here, in our own galaxy, it is possible that a Cepheid that looks brighter only looks brighter because it is a lot closer to us than another one which is dimmer. So that you could make rules about the Cepheid variables in the Magellanic Clouds you couldn't safely make with the Cepheids in our own galaxy. Well, they could make rules, and these rules were then used with certain complexities, which I can't go into, to account for the distances of objects in the galaxy. In other words, you look at each globular cluster, find the Cepheid variable in it, detect its period. From its period, you know how bright it is, really. And from its apparent brightness in the telescope, you can figure out its distance. The American astronomer Harlow Shapley calculated the distance of all the globular clusters he could measure, and he discovered that they were distributed spherically about some point in the galaxy. Here is the solar system. I'll make an X. Here are a series of globular clusters which I will make with zeros. They're all centered about this point here. And that's why we see all of them in one part of the sky and nothing in the other part. Why should the globular clusters be centered around some point far away from us? Only because that point far away from us is the center of the galaxy. We are not at the center. We are far from the center. But then in that case, why does the Milky Way look equally bright all the way around? Why doesn't it look much brighter, much more complex, much more luminous in the direction of the center? And it turns out that there's one thing in the Milky Way that the earlier astronomers hadn't figured out. Dust clouds. We suffer from a cosmic smog problem. And all we see is our end. In our end of the galaxy, it looks as though the Milky Way is equally bright all around, because the more distant reaches we can't see, except by indirect methods, like studying the globular clusters. Therefore, in the 20th century, we determined that our galaxy is 100,000 light years in diameter, not merely Herschel's 8,000, 12 times as wide. 100,000 light years in diameter. And the thickness at the center is not 1,500 light years, but 3,000 light years. Beg your pardon, 30,000 light years. And it doesn't have 300 million stars in it. It has over 100 billion stars in it. In short, we are 30,000 light years from the center. We are in the arms, at the edge, close to the edge of the galaxy. Well, then you see the picture we have, which we developed by the end of the 19th century and the beginning of the 20th. We have altered the picture as it was from the beginning of the 19th century, when the stars were still at an unknown distance, when it was still possible, even if not very likely, that the sky was just a shell, a solid sphere, and that the stars were just little thumbtacks stuck into it, and that the whole might be just beyond the solar system, and that the whole diameter of the entire universe might be only a few billion miles. We now see that we have a vast collection of stars, over 100 billion, distributed through a lens shape, 100,000 light years in diameter, with the sun and its attendant planets, not even anywhere near the center, but far out in the suburbs. We have a picture of a universe which puts us completely in the shade, a vast realm that is more poetic in its immensity and its complexity than anything mere poets could imagine, worked out entirely by practical scientists working with the observations they made through the telescope. And as the 20th century opened, it seemed reasonable to suppose that this enormous galaxy, with this vast number of stars in it, was indeed all the universe there was. That at last mankind had penetrated to the end. It was a respectable universe, enormous, and there was no reason to think anything lay beyond the galaxy. And they were wrong, because as it turns out, our galaxy is only the beginning. As our sun is a mere speck of matter in the galaxy, so our galaxy is a mere speck of matter in the greater universe. And beyond our galaxy lay realms undreamed of in 1900. Beyond our galaxy lay phenomena that no one imagined. Poetry is greater than anything within. And it is to this vast universe beyond the galaxy that I will turn in my last lecture, to be given day after tomorrow. Thank you.